Hi everyone. Today we're going to discuss chemical reactions as well as calculations involving chemical reactions. So previously we learned about the mole concept and we were converting between moles, atoms, and mass. And today we're going to apply the mole concept to balanced chemical equations, and we're going to calculate mass relationships in chemical reactions. So down below we have a flow chart for these types of problems. So for instance, if we start with grams of a substance, we can convert that to moles using the molar mass, also known as the atomic, molecular, or formula weight. And then once we have the moles of substance A, we can convert that to moles of another substance that we're interested in using equation coefficients or ratios. And then once we have moles of B, our other substance, we can convert that to grams using the molar mass of B. So we're going to use this flow chart a lot today. And before we do that, let's consider the following balanced reaction. So here we have 2 H2S reacting with 3 O2 to produce 2 SO2 plus 2 H2O. So this equation has already been balanced for us, and the reason balancing equations is so important is, again, we want to make sure we're following the law of conservation of mass. So we want to have the same number of atoms on both sides of the arrow. But additionally, this can tell us the ratio of reactants to products. So the mole concept can be used to write useful statements that will be the source of factors needed to solve numerical problems. So the following are 3 of the possible statements we could make. So for instance, we could say 2 moles of H2S reacts with 3 moles of oxygen to produce 2 moles of SO2 plus 2 moles of H2O. Or we could also say that 2 molecules of H2S are reacting with 3 molecules of O2 to produce 2 molecules of SO2 and 2 molecules of H2O. So those are the same. We could interchangeably use moles and molecules there. Or maybe we want to write this in terms of mass. So if we have 2 moles of H2S, that is equal to 68.2 grams of H2S. If we have 3 moles of oxygen, that would equal 96 grams of oxygen. And when those two amounts react, we should end up with 128.2 grams of SO2, which is equivalent to 2 moles of SO2, and 36 grams of H2O, which is equivalent to 2 moles of H2O. Now, additionally, if we add the masses on the left-hand side, those should equal the masses on the right-hand side because of the law of conservation of mass. So we're going to use all of this different information in order to solve some problems. Now, before we do that, let's review the factor unit method. So remember from a while back, there were a few steps we followed in the factor unit method, or dimensional analysis. So step 1, we write down the known or given quantity. And then we include both the numerical value and units of the quantity. And then we leave some working space and set the known quantity equal to the units of the unknown quantity. Then we want to multiply the known quantity by one or more factors such that the units of the factor cancel the units of the known quantity and generate the units of the unknown quantity. So we want the given unit to be in the denominator of our factor and the desired unit to be in the numerator. And after you generate the desired units of the unknown quantity, do the necessary arithmetic to produce the final numerical answer. Okay, so hopefully this is all review and kind of coming back to you. And now let's actually go through an example. So we're going to calculate the number of moles of H2S that would need to react with excess O2 in order to produce 115 grams of SO2. So we're going to use the equation that we saw earlier, where 2H2S reacts with 3O2 to produce 2SO2 and 2H2O. Okay. So we are told that we want to produce 115 grams of our SO2 product. And we want to determine how many moles of H2S we need in order to produce that amount of product. And then we're just going to assume that we have excess oxygen, which just means that we have enough oxygen to react with H2S and however much we might need. So maybe it's just reacting with oxygen in the air, which means we have a bunch of oxygen present. So it's not going to limit how much product we form. All right, so our plan of attack here is to use that flow chart that we saw earlier. So we're going to start with what we know, which is we have 115 grams of SO2. And then we want to convert that to moles, because remember, we can't directly relate masses to each other. We have to go through moles first. So we have to figure out the relative amounts of each reactant and product first. Now, in order to go from grams to moles, we need the molar mass of SO2. So we'll do that calculation in a bit. And then to go from moles of SO2 to moles of H2S, we will need to use the ratios or coefficients from our balanced equation. Okay, so that's our plan of attack. Now, before we actually perform this calculation, let's determine what the molar mass of SO2 is. Okay, so if we pull out our periodic tables, sulfur has a mass of 32.06 grams per mole. And then we're going to add 2 times the mass of oxygen because we have 2 oxygens. So that's 16 or 15.999 grams per mole. And then we're just going to plug that into our calculators. And we should find that the molar mass of SO2 is 64.06 grams per mole. So now we can use that to convert from grams of SO2 to moles of SO2. And then the other component we need is the ratio between SO2 and H2S. So looking at our equation up above, we have 2 H2S for every 2 SO2. So there's a ratio of 2 to 2, which is really just 1 to 1, between H2S and SO2. So that's what we'll use for the second calculation. Okay, so let's put this all together. All right, so we'll start with 115 grams of SO2. And then we're going to use our molar mass of SO2 to convert to moles of SO2. So that means we want moles in the numerator because that is our desired unit for the first step. And I'm going to write SO2 there just so I know what I'm actually calculating. Otherwise, it can get a little confusing sometimes. And then in the denominator, we're going to put the mass for 1 mole of SO2, which we calculated, and that was 64.06 grams. And again, I'm just going to write SO2 next to that so it's a little bit easier to follow. And we could stop there and figure out how many moles of SO2 we have, and then carry that over into our second step. But I'm just going to write one long equation here because that will help me see the cancellation of units a little bit better. Now in the second step, we're going to convert moles of SO2 to moles of H2S. And remember there was a 2 to 2 ratio. Now we want moles of H2S, so we'll put that in the numerator. And in the denominator, we'll put 2 moles of SO2. Okay, so let's make sure our units cancel. So grams of SO2 will cancel with grams of SO2, and then moles of SO2 will cancel with moles of SO2. So our final unit will be moles of H2S. So actually, I'm going to rewrite this as 115 times 2 divided by 64.06 times 2. And our final unit is moles of H2S. Okay, so in our calculators, we would plug in 115 times 2 divided by 64.06 times 2. Now remember to put parentheses around everything in the denominator, otherwise your calculator might assume that you're multiplying by 2 at the very end of the calculation. So unfortunately calculators are not as smart as we would like them to be, so we kind of have to tell them exactly what we're doing. Alright, so once you plug that in, you should get a value of 1.80 moles of H2S. And I did round my value so that I would have 3 sig figs, because in the very beginning of the problem, we had 3 sig figs. And molar mass in terms of sig figs are a little tough because it depends on your periodic table. And then 2 to 2 was an exact ratio, so we don't consider those for sig figs. So we're really just considering that first value. So our final value should have 3 sig figs. Okay. So hopefully that helps a little bit with seeing how we can use balanced equations in calculations. Now let's do a couple more examples so that we can see some other ways we can use this information. And here's a solution slide if you need it for later. So another example, a chemist starts with 30 grams magnesium and excess oxygen. How many grams of magnesium oxide are expected to form? And the balanced equation is given below, where 2 moles of magnesium react with 1 mole of oxygen to produce 2 moles of magnesium oxide. Okay, so we're told that we are starting with 30 grams of magnesium. We have excess oxygen, so we don't have to worry about how much oxygen there is. And we're going to try to determine how many grams of magnesium oxide will be produced. All right, so our plan of attack, we're going to start with the 30 grams of magnesium. And the first step will always be convert to moles if you have grams. So we're going to need the molar mass of magnesium, which we can just look up on the periodic table. And then in the second step, we're going to convert moles of magnesium to moles of our product, magnesium oxide. And we're going to use the ratio from our balanced equation. And then in the last step, we're going to convert moles of magnesium oxide to grams of magnesium oxide. So we'll need the molar mass of magnesium oxide. Okay, so probably the first thing we want to do is calculate the molar mass of magnesium oxide. Okay, so looking at a periodic table, the molar mass of magnesium is 24.305 grams per mole, and the molar mass of oxygen is 16 grams per mole. So adding those together, the molar mass of magnesium oxide is 40.305 grams per mole. Okay, and then for the molar mass of magnesium, we already saw that that is 24.305 grams per mole. And then the ratio will just be 2 to 2, or 1 to 1, if we simplify it. All right, so let's calculate how many grams of magnesium oxide will form in this reaction, or I guess what we expect to form. There's always errors that occur in reactions, so we don't always form what we expect, but it's still a good idea to just see how much you expect to form. Okay, so we're going to start with our 30 grams of magnesium. And in the first step, we want to convert grams to moles of magnesium. So in the numerator, we'll put 1 mole of magnesium, and then we're going to divide by the mass of 1 mole of magnesium, which is 24.305 grams. All right, and then in the second step, we're going to use our ratios between magnesium and magnesium oxide, because we're trying to convert from moles of magnesium now to moles of magnesium oxide. So we said that there are 2 moles of magnesium oxide for every 2 moles of magnesium. And again, that's just from our balanced equation. And now in the third step, we're going to convert moles of magnesium oxide to grams of magnesium oxide, and we're going to use the molar mass that we calculated on the last slide. So in this step, we want to end up with grams, so we'll put 40.305 grams of magnesium oxide in the numerator, and then we'll divide by 1 mole of magnesium oxide. Okay, now let's make sure that all of our units cancel properly. So grams of magnesium cancels with grams of magnesium. Moles of magnesium cancels with moles of magnesium. Moles of magnesium oxide cancel with moles of magnesium oxide. and we'll be left with our desired unit, grams of magnesium oxide. So let's kind of simplify everything. So we have in our numerator 30.0 times 2 times 40.305. And in the denominator, we have 24.305 times 2. So you could cancel the 2's because, there's one in the numerator, one in the denominator, so they do cancel, and that would further simplify the problem. And then our final unit is grams of magnesium oxide. So if we plug that into a calculator, we should have a value of 49.8 grams of magnesium oxide. So we're expecting approximately 50 grams of product. And later on, we will talk about how that doesn't always happen. Typically, errors occur in lab. Maybe we lose some of the product or some of the reactant somewhere down the line. So we're probably not going to end up with that much product. We're probably going to end up with less. But again, we can use our balanced chemical equation along with molar masses to try to predict how much product we could make. All right, so let's do one more example. Let's say a chemist needs to produce 55 grams of carbon dioxide. How many grams of CH4 or methane should they start with? Assume they have excess oxygen. So our equation is shown below, and it's already balanced for us. But CH4 is going to react with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of H2O. All right, so we're really just interested in the product CO2. So we're going to just ignore the other product for this problem. And we're also just interested in the reactant CH4 because we have excess oxygen again, so we're not as concerned with oxygen here. And let's see, we want to end up with 55 grams of CO2. So we want to try to determine how much or how many grams of CH4 to start with. Okay, so our plan of attack again, very similar to the last problem and the one before that. If we start with 55 grams of CO2, we first want to convert that to moles of CO2. And in order to do that step, we're going to need the molar mass of CO2. And then in the second step, we're going to convert moles of CO2 to moles of CH4, which is what we're interested in. So we'll need the ratio between the two. And then finally, we can convert moles of CH4 to grams of CH4. But to do that, we need the molar mass of CH4. Okay, so let's calculate the molar mass of CO2 and then the molar mass of CH4. Okay, so starting with CO2, the molar mass of carbon is 12.01 grams per mole. And then we're going to add 2 times the mass of oxygen, since we have 2 oxygens there. So plugging that into our calculator, we should find that that is equal to 44.01 grams per mole. And now for the molar mass of CH4, methane. Remember, methane is what's present in natural gas. So again, the molar mass of carbon is 12.01 grams per mole. And then we have 4 hydrogens. So we'll multiply 4 by the mass of hydrogen, which is 1.008 grams per mole. Okay, so plugging that into our calculator, we should find that the molar mass of methane is 16.04 grams per mole. Okay, and then we already saw that our ratio between CH4 and CO2 is just 1 to 1, so that will be super easy. All right, so let's put this all together. So starting with our 55 grams of CO2, which is what we want to produce, we're going to convert that to moles using our molar mass that we calculated. So we'll put 1 mole of CO2 in the numerator and 44.01 grams of CO2 in the denominator. And then in the second step, we want to convert moles of CO2 to moles of CH4. And remember, there's just a 1 to 1 ratio between those. So we'll put 1 mole of CH4 in the numerator and 1 mole of CO2 in the denominator. And then in the last step, we're going to convert moles of CH4 to mass. So we're going to multiply by the mass of CH4, which is 16.04 grams, and we're dividing by 1 mole of CH4. Okay, so let's make sure our units cancel. So grams of CO2 will cancel with grams of CO2, moles cancel with moles, and then moles of CH4 will cancel with moles of CH4. So we get our final desired unit, which is grams of CH4. So putting this all together, in the numerator we have 55 times 16.04, and then in the denominator we have 44.01. And our final unit is grams of CH4. All right, so plugging that into our calculator, our final answer should be 20 grams of CH4. Okay, so we should start our reaction with at least 20 grams of CH4. Because remember, we might not actually produce the total 55 grams of CO2. So in a way, this equation is more telling us that we should at least start with 20 grams, but maybe we should start with more just to make sure we actually produce 55 grams of CO2. Okay, so I'll post a worksheet that goes over a few more example problems, and I'll also post the key so you can get a little more practice in and then see if you get the right answer. Additionally, next time we'll talk about limiting reactants. So if we only start with a little bit of each reactant, how much product will we actually end up with? So we'll go over that next time. I'll see you then.